Creep is a progressive time-dependent plastic deformation where a material is subjected to constant values of load or stress. This is a typical strain versus time creep curve. In the initial stage, that is primary creep, the strain rate is relatively high, but slows with increasing strain. This is due to work hardening. The strain rate eventually reaches to minimum and becomes constant. This is due to the balance between work hardening and annealing, that is, thermal softening. This stage is known as the secondary stage or steady state creep. This stage is most understood. The characterized creep strain rate typically refers to the constant slope in the secondary stage. Stress dependence of this rate depends on various creep analysis. In tertiary creep, which is of not much importance as far as practical applications are concerned, the strain rate exponentially increases with stress because of nicking phenomena. This rate of deformation is a function of various parameters, which are as follows. First, material properties like grain size, dislocation density, equicohesive temperature, activation energy, etc. Second, exposure time. Third, temperature. Fourth, applied load or stress. The effect of the forementioned factors on creep can easily be elucidated through a mesoscale lump order developed on the platform Microsoft C++ Visual Studio. We considered the general microstructure of metals and alloys to be consisting of different types of obstacles which have varied strength defined by strength coefficient S and characteristic slip probability peak. Simple rules as mentioned in the modeled formation are used to ensure of compliance with mechanical equilibrium and compatibility. The mechanistic details of the deformation do not have to be explicitly considered in order to develop model for how metals deform in general. So this model acts as a black box where certain parameters and wisely chosen constants are fed into the Arrhenius activation equation dependent on activation energy barrier delta G, and graphs are generated by simulation for a particular metal alloy system. Following are the results. The normalized creep curve shows as the homologous temperature increases from 0.25 to 0.8, the slope of the steady state region, and hence the steady state increases, while at the constant homologous temperature of 0.6, the steady state creep rate increases with applied external load, exemplified by the following table. Since obstacle distance is inversely proportional to the obstacle density, grain size reduction can simply increase the resistance to dislocation movement. As the obstacle distance increases from 0.6 micrometer to 1.10 micrometer, which is analogous to increase in the grain size, the steady state creep also increases. Thank you.